a very important topic in the theory of linear algebra, which is the topic on eigenvalues and eigenvector. I'm pretty much sure that you already know some bits of the eigenvalues, the theory of eigenvalues and eigenvector, or at least you know that for a given matrix how to compute the eigenvalues and eigenvectors, and what are some of benefits of calculating it, and you might also have some of the applications of it actually. I mean, if not, what we're going to do in the upcoming few set of discussions, we're going to extensively cover the theory of eigenvalues and eigenvector. We will investigate the basic facts about eigenvalues and eigenvectors. Then we will move on to some of applications of it, that how they can allow you to diagonalize the matrices, and how they allow you to create, for example, allow you to compute the Jordan normal form, which is a pretty important topic from the application point of view, and we will also talk about some of very concrete applications of the eigenvalues and eigenvectors actually. So whenever, for example, you are making a Google search, you see that Google has kind of a magic wand actually, or some kind of algorithm, some kind of a very interesting algorithm, that whatever search you are making, in the first few results, you will find your most relevant websites actually. Now, how does Google find and ranks these websites? So there is a algorithm working behind at the Google search, or it was working at least some years ago behind the Google search. That algorithm is called the PageRank algorithm. It is based on a lot of mathematics. For example, it involves some of the probability theory, it involves some bits of calculus, and it also involves some bits of linear algebra. So when you are making a Google search, next time say thanks to the eigenvalues and eigenvectors, because what the Google page algorithm is, Google PageRank algorithm is doing at the back end, is that it is solving basically an eigenvalue problem. It is trying to find the eigenvector corresponding to a matrix, corresponding to an eigenvalue 1 actually. So we will talk about that as well. So the applications of eigenvalues and eigenvectors are always there. It has a lot of applications in theory of differential equation, applications, for example, in data compression, in data analysis, in statistics. It's the single most important topic of the linear algebra that has so much and so applications in the variety of sciences that no other topics in linear algebra have that much applications actually. So it's a pretty exciting topic, so we should focus on it actually. So let's start. So what we will like to do in today's discussion, we will like to define what do you mean by the eigenvalues and vectors, and we will try to visualize them. Okay, we will try to see them through some of the examples. We would like to answer this question, that does every matrix has eigenvalue and hence eigenvector? Okay, does every matrix has eigenvalue? The answer is yes. We will prove it in the form of a theorem actually. Then we will move to a very natural question next, is that okay, if there is an eigenvalue of matrix, how many are the eigenvalues of the matrix? Matrix. So how many are the eigenvalues of a given matrix actually? Okay, and we will also try to discuss in today's discussion that if there okay, so this is also an interesting question that we like. Is there something special about? Is there something something special about, say, a matrix A, okay, if it has a maximal, okay, a maximal number of different eigenvalues, maximal number of different eigenvalues. Okay, so we will try to basically answer these questions in our today's discussions actually. So we'll try our best to answer all of these questions. I mean, if not, maybe we can cover these on the next as well. Okay, so let's just start with, for example, the definition of the eigenvalues. I hope you already know the definition, and we'll try to interpret it in many different ways. So if you have, say, a given matrix, n by n matrix, say with entries from F, which may be real or complex, then a number lambda from, say, set of complex number, and a vector x, okay, that is a non-zero, and vector x that is non-zero, then so you have a matrix and a number lambda and a vector non-zero. We're going to say that a pair lambda x, okay, this pair is an eigenpair, okay, so it's an eigenpair of A if it satisfies this equation Ax equal to lambda x actually. Okay, so if it so a pair, a complex number and a non-zero vector, you're going to call this pair an eigenpair if it satisfies this interesting equation. Let's call this equation the equation star actually. And if an eigenpair satisfies this equation, then I'm going to say that lambda is an eigenvalue of matrix A, and x is the corresponding eigenvector to the lambda. So x is an eigenvector, okay, of A corresponding to the lambda actually. Okay, corresponding to the eigenvector lambda. Now you can interpret this equation star in several different ways actually. Okay, so you can interpret it as that it is a kind of a vector. Okay, so eigenvalue, eigenpair, so lambda x is kind of a pair for which Ax is lambda x. So what would be the interpretation of Ax? So x is a kind of a vector which is, if you treat, for example, A as a transformation, okay, so it's a kind of a transformation. So if you transform the vector x under A, you're gonna get a copy of the vector x actually, okay, but that copy is basically multiple of the vector x. So if you, for example, transform x under the matrix A, you can get, what do you call, twice of this vector, or you can get half of the transformed vector. So it could be 1 upon 2x, it could be negative x, it could be, you know, what do you call, it could be, say, 1/3 of the x. So if x is some vector, okay, you transformed it under the matrix, so the matrix A kind of returns the same vector actually, but this same vector can have a bigger size, okay, can have a bigger size, it can have a smaller size, even so if lambda is negative, it can have a change, you know, what do you call, direction as well, but it should be parallel to what do you call the vector x actually. Okay, so this could be one of the basic interpretation of the eigenvalue equation actually, that x is, we are interested in finding those vectors which are kind of invariant under the matrix A. Okay, so saying invariant is really a stronger term, but we are interested in those vectors. If we transform those vectors under the matrix A, you get the version of the same vector. Okay, it could be smaller, it could be bigger, it could have an inverted direction, but it returns the same vector actually. Okay, some version of the same vector. Okay, it could be half, it could be full, it could be, you know, precisely the same vector. Okay, or lambda can be a complex number. Okay, lambda can be a complex number. So this is really the definition of what do you call eigenvector actually. They can be, so this is important to keep in head, that an eigenvalue can be 0, but eigenvector cannot be a 0 vector. It must always be a non-zero vector actually. What are some of the, say for example, the basic remarks about, say, this definition, what follows from, say, immediately. So here is the first remark about, for example, this definition, that if, say, lambda x is an eigenpair, so it's an, say, eigenpair, okay, then, and you take, for example, a number c does not equal to 0, then we know that since lambda x is an eigenpair, so it satisfies this equation actually. So now if you transform a vector, say cx under A, okay, transform a vector cx under A, which is a multiple of the vector x, then I can write this as c times of ax, so c is a constant, you can pull it out, okay, and this is going to be c lambda x, or you can write it as lambda times what you call cx actually. So this also shows that lambda cx is an eigenpair actually. So it's an eigenpair. So what is the conclusion from it? The conclusion from here is that a single eigenvalue can have a lot of eigenvectors corresponding to it actually. Okay? So a single eigenvalue can correspond to what do you call a lot of eigenvectors. Okay, so if lambda has an eigenvector x, then any multiple, scalar multiple of this vector is also an eigenvector corresponding to the lambda. But now you can ask other way around actually. Can we have two eigenvalues corresponding to a single vector? So in other words, imagine lambda x and say mu x are two eigenpairs. So can we have lambda x and the mu x, you know, lambda and mu, the eigenvalues corresponding to eigenvector, the same eigenvector x actually? The answer is really no. Why? Because if you take, for example, so since this is an eigenpair, they are eigenpairs actually. So if you take, for example, lambda x, okay, lambda x, I know that this is going to be ax, but this ax is also mu x actually, because mu and lambda are the eigenvalues of the matrix A corresponding to eigenvector x actually. So this means that if you take this on the other side, lambda minus mu operated onto x or multiplied by x would be 0. But since x is non-zero, what follows from here that lambda minus mu must be 0, and hence lambda must be equal to what do you call mu. So what does this shows? An eigenvector corresponds to only one eigenvalue. okay, while one eigenvalue can correspond to many eigenvectors. So corresponding to one eigenvalue you can have many eigenvectors, but corresponding to one eigenvector you can always have one, what do you call, eigenvalues. So with this definition, and say for example these two basic facts, we would like to, you know, do all this stuff actually. Let's visualize what you call the eigenvalues and eigenvectors, and then we would like to, you know, answer the question that does every matrix has an eigenvalue? How many, I mean, okay, if every matrix has an eigenvalue, how many can be the, what do you call, eigenvalue for a given matrix? Okay, and does eigenvalue tell you something special about, or the number of eigenvalue tells you something special about the matrix A actually? Okay, matrix A, the answer is that it does actually. It actually explains the very fundamental structure of the matrix actually. So if you know the eigenvalues, you know the matrix actually. So you know really the core or the fundamental of that given matrix. So let's talk about some of the examples of eigenvalues and eigenvectors, and let's try to, what do you call, visualize them actually. Okay. So let's try to visualize them. Say for example, the first example is that if you take, say, identity matrix, okay, so if you take identity matrix, then we know that Ix is equal to x, okay, so for all x actually. Okay, so what does this show? That for this given matrix I, identity matrix, okay, 1x is eigenvector. 1x is eigenvector. In other words, every single vector, okay, in Fn, okay, in Fn is really, what do you call, an eigenvector corresponding to the eigenvalue 1 for the given matrix A actually. So this is the first example. Let's do, what do you call, an interesting example. So let's consider matrix A, okay, and that goes like -3, 0 and 0, 2. Okay. Now I can write this -3, 0 as a, you know, as a column matrix, as a matrix 3E, in which the first column is 3E1. In other words, E1 is 1, 0, 1, 0, and -3 multiplied means -3, 0, and 2 E1. Okay, so this is what is really the eigen matrix, the matrix A. So hence you can deduce from here that if you take the matrix A and multiply it with E1, okay, so in other words, take this matrix and multiply it with 1, 0, you're gonna see that you're gonna get 3 E1. Okay, and if you take the matrix A and multiply it with, say, E2, you're gonna get, what do you call, a vector which is 2 E2. Okay, so this is what that you're gonna get for this. So what does this show? This shows that, you know, -3 E1 and 2 E2 are the two eigenpairs of, what do you call, of the matrix A actually. But there's a very interesting kind of a visualization of this matrix. So if I correspond, so what would be the transformation corresponding to this matrix A? Okay, so if I, for example, take a matrix A, okay, and I want to write the linear transformation corresponding to the matrix A, so it's going to be the matrix AX actually. Okay, so if X is, say, XY, okay, so the AXY is really going to be -3, 0 multiplied by this, so it's going to be -3x and 2y. So this is going to be really the linear transformation corresponding to the matrix A. Okay, Now if you try to visualize this linear transformation, in other words, if you try to see that how this matrix is operating on a point or a vector, say in space, so let's see, for example, let's see the visualization of it actually. So imagine this is my vector E1, okay, and this is my vector E2, okay, and this is, say, the triangle spanned by the what do you call the vector E1 and E2 actually. And let's make, for example, a smiley face in that, okay. So this is a region, for example, in 2 dimension, okay, so it's a collection of the points which are kind of can be written as the linear combination of E1 and E2. What I would like to do, I would like to transform this region or this picture under the matrix A or under the linear transformation, what do you call A. So what do you think what you're going to get? So you're going to get something like this actually. So the first thing that you're going to get is that E1 is transformed into minus 3 times of E1, okay. So if this is E1, this is E1, take the 3 copies of it and invert them. So 1, say 2, and say 3. So this is like minus E1, minus E2, minus E3. So this is so this vector, okay. So this vector is really what do you call minus 3E1, okay. So under the matrix A or under the transformation TA, E1 is transformed into minus 3E, and E2 would become the double actually. So if this is 1 E2 and this is E2, so this is really what do you call 2 E2, okay. And now let's see the region that is spanned by these 2 vectors actually. Now can you guess that how does this picture is going to transform, okay. So one of the things that is going to happen is that this picture is going to invert, okay. So one thing that is going to happen is that this picture is going to invert. How it is going to invert? That this is going to, so for example, okay, so in order to show this, so this is really, okay, so one of the trouble is that this picture is symmetric actually. So let's make it a bit more asymmetric, okay. So say this eye is circular and say this eye is really, so maybe he's blinking his eye actually. So when this picture will be transformed under this transformation, so what will happen? So first thing would be that since this E1 is flipped, so this would be flipped actually, and the E1 is stretched. The height would be double, okay. The height of this is going to double, and since the E1 has been tripled and inverted, so what will happen is that this picture will be inverted and then tripled and stretched actually. So this picture would, say for example, look like something like, okay, this actually, okay. So let's assume that this has been stretched 3 times. So this is 1 time, and this is like, this has been stretched, horizontally 3 times, and vertically it has been stretched twice actually, okay. Vertically it has been stretched twice, and the picture would look like, what do you call this, okay. Would look like this, something like this actually, okay. It's something like this, alright. So instead of, for example, taking this picture, if I take, for example, B, the B which you put, for example, put it in a box, will be transformed into, what do you call, a B that has, for example, thrice as the size of this, okay. So this is stretched thrice, okay, maybe this is say stretched thrice of this, and the height is twice of this actually. Okay, so twice of this actually. So you can interpret it that. So this would be stretched thrice horizontally, flipped. So the minus picture shows that it is just flipped, then stretched horizontally thrice. The size of this, in other words, the diameter of this is 1/3 of the diameter of this, or this is the 3 times of the diameter of this actually. Okay, so something like that. And say the diameter vertically so the diameter of this is really the double of the diameter of this circle actually. Okay, so this is a transformation that kind of produces this picture actually. Okay, so now you can see actually that the eigenvalues are playing a role in visualization actually. Okay, in visualization of picture. So when you are, for example, on your screen, if you are, say for example, turning a picture or rotating a picture with say angle 90 degree or 180 degree or some degree, basically, and say for example if you are zooming it or zooming out, you are actually playing with some matrix, and you are actually playing with the eigenvalues of that corresponding matrix actually. So let's talk about, for example, another matrix. Okay, let's talk about another matrix and see that what that matrix mean. So here is another example. Okay, so this matrix is 1 1 1 1. Okay, so you can write this as, so how can I write it? Okay, how can I write it? I can really